Hello everybody, welcome to the World of Control channel. I'm Muhammad, and in this last video about designing and training a neural network for identifying the dynamics of the inverted pendulum, I'm here to evaluate and test our trained neural network that we designed in the previous video to see if our neural network can identify our dynamics. Okay, let's see what we have. In the previous video, as we see, I saved our neural network in the net underscore pendulum identification.mat here. So now I want to write another M file to actually test our neural network and see if our neural network can actually identify our dynamics. Okay, CLC clear close all. I will save this as test nn test underscore nn pendulum. Okay, first of all, I need some real data. I need some test data actually. So I want to first open my Simulink model and run it, save my test other data, and after that test my actually evaluate my neural network. Okay, so the first section is create the test data. Okay, first of all, we use open command to open our simulation. The name of our simulation is this dynamic underline pendulum in underline English, and we can simulate it with the command of sim here, so we can have our dynamic pendulum here, and if we run this, we can see that our simulation has been opened and has been run, and we can see that we have our out here. Out has actually our input and output data here. Okay, we can say that out.u dot signals dot values is our data, is our input data, and y is equal to out dot actually y that signals. Let's run it to see if our code works. Actually, it is working, but our output has to be modified because it is a matrix of three-dimensional matrix. So we can say that y is equal to all of the y, and this line will modify our actually dimension of our output to be as the same as our input u. Okay, now we have our input and output test. Okay, the second part is to modify our input and now we know that we can use the function modification that we wrote in the previous videos to modify our inputs of our neural network actually. Okay, we can say modification, it will get our inputs, our outputs, and our order. Our order has to be the same as the trained neural network that we trained actually. We can see that we trained our model with the order of 10, so we have to use 10 here to actually use our data for our neural network. The next step is to importing our trained neural network. So we will say import neural network, import neural network, and I will say net underline pendulum is equal to load and we say net underline pendulum identification.mat. That is our trained actually neural network. Okay, now we can use our neural network to identify the output of our dynamics, which is theta here. Okay, so we can write creating predicted output, and now we can say y hat that represents of our predicted output is net underline pendulum of our u underline modified and our output that we want to predict and identify and the order. Actually I think let's run this for now to see how it works. Okay. You underline modify. Oh, I forgot to transpose it because the samples of our input and output has to be on the columns of the actually inputs and outputs of neural network. So I think I have to give our network just the actually inputs of our test data. Let's see if there is any problem. Yes, it has. Let me import y transpose and order to see if our model works. Index in position 1 is invalid. Why? Why is it invalid? Modif. Oh, I need the size of it, not the 10,001. Okay. And why? size of y is this. Oh, okay. Let me delete the order to see if our model works. In this situation, we have to check. We have to check the help of the Matlab to see what is the problem. Net underline pendulum is okay. U underline modif int y. Let me see if it works. It works with this input. No, it doesn't. Why? Array, and this is must be positive integers or logical values. There is a problem now. I have to understand why this is happening. Why doesn't it work here? Let me check if I can understand the problem of our code. Okay, our network will. Oh, I understand. I think. Okay, I understand. When we import our neural network, it is imported as a structure. So we can see that net underline pendulum is a structure, but in this structure actually is our real network. So when we load our structure of neural network, we have to say dot net, and now our network is ready. Let's see if it works. Okay, it is working. So now we can compare y hat, that is the predicted output, and y, that is our real output, with each other to see if our neural network is identifying our dynamics of our system. Okay, let's open a blank figure here, and say plot. Actually, we have to, if we see here, the u has a parameter called time dot time, I think. Let's see if it works. Oh, I think time has to start with a letter, small letter. Yes, it has to be small here. And now we can plot our real y and real output actually with respect to the time here, and say hold on, because we want to plot our predicted output in the same plot, and we can plot y hat and if we run this we can see that our simulation has been opened. What is the problem here? dot time. Oh, out dot u dot time. I have to say out dot u dot time. Okay, let's see what is the problem now. We do not have time. Oh, the time has to be with the capital T here, and if we run it again, oh, we can see that we actually identify our dynamics of our system here. If I zoom in, we can see that we have two plots that are very, very, very similar to each other. And actually they are very similar to each other. Let's make the legend on here. Let's make the legend on here. The first one is real output, and the second one is identified output. And actually we can write X label and Y label for our system. Okay, and we can have a title for our figure. Comparison of real outputs, real theta actually, and the identified theta. And if we run this simulation again, now we can see that we are identifying the dynamics of our system. But this data is our train data. A very, very, very important property of neural network models and identification using MLP models is that if you change your input to anything, the neural network will predict your outputs and will identify your actually dynamics. So for now, I want to change my input signal to be, for example, I don't know, a sawtooth with amplitude of 10, and see if our neural network can identify our output and actually our dynamics of our system. Okay, it didn't, because I think I make our amplitude a little bit large here. Let's see if we can have our, yes, we can see that our real output is the blue actually figure here, the blue line here, and the identified output is the red one. We can see that our neural network can identify our dynamics very well. But what we saw in the previous example was if we choose our amplitude or our input, some inputs that are very large or are not in the domain of our input data that we trained with, our neural network can't identify our uh, system. Let's change the input to be, for example, sine wave to see if our neural network can identify our dynamics. And now we can see that actually our neural network is identifying our system very, very well with very small errors here. You can see that uh, the identified output, actually identified theta, is very, very similar to the real data and real theta actually. So we can conclude that we have a neural network here. We actually trained a neural network, an MLP model that represents and actually knows the dynamics of our inverted pendulum. So we can use this method to actually identify other complicated systems with different inputs, multiple outputs, and we can see that this method can work for much more complicated systems. In this channel, I will make other videos about identify different other complicated systems with much more complexity and uh, different number of inputs and outputs, and I will upload in this channel. Uh, and thank you very much that you see this video. Please make sure that you subscribe this channel, because I will make um, such these videos about modeling and controlling and identifying different other systems and controllers. Thank you very much.